So let's start with T1 versus T2. Very similar sequences, and people get tripped up a lot with these. So between T1 versus T2, we've got two basic rules that differentiate the two. Number one, within a given sequence, so take T1 for example, water and fat are opposite signal intensities. Number two, between sequences, T1 versus T2, a given substance, take fat for example, will have opposite signal intensities. This will make sense in a minute. And let's start with T1. Here's our T1 image. How do we recognize T1? Well, in T1, fat is bright, water is dark, and new blood is bright. And this is useful for anatomic details. We can pick up vascular changes and disruption of the blood-brain barrier when we add in contrast. So let's take a look over here at the image. So water, or CSF, is dark, and fat is bright. So areas where there's a lot of myelin, these deep white matter tracts, are going to show up bright, whereas outer cortex is not. This isn't the best image to demonstrate this, but you'll see the differences when we move on to T2. So let's pull up our T2 image. How do we recognize it? Well, everything is flipped. So now fat is dark. These highly myelinated areas here, which are fat, are dark. Water is bright, so look at our CSF right here in the ventricles. It's pretty bright. But flow is dark, and this is called flow void. So where there's fluid moving at a high velocity, so take a blood vessel for example, it's going to be dark, and that's important to remember. What is the sequence useful for? Again, anatomic details. I think T2 is probably a little bit better than T1, especially our CSF spaces here. It's useful at picking up most lesions kind of in general. One area where it can trip up a little bit is when you have lesions or edema really close to CSF spaces, because they'll both be bright. Okay, so let's compare these two. We've got T1 here and T2. So fat is bright on T1, fat is dark on T2. CSF is dark on T1, bright on T2. Got it? Alright, let's move on to Flair, which stands for Fluid Attenuation Inversion Recovery. Sounds confusing, but that'll make sense in a minute. So here's our Flair image. I like to think of Flair as basically a T2 image, but the CSF spaces are flipped back to being dark or hypo-intense. So if we look here, it looks just like a T2 image. So for example, these deep basal gangliostructures here, which don't have as much fat in them, are looking pretty bright. Fat is dark, but the CSF is also dark. Interesting. Also, non-free-flowing water is bright. That'll make sense in a minute. Fat is dark, already went through that. So what is this useful for? Same as T2, but it does a better job of delineating lesions near the ventricles, because edema would be bright, but in Flair, the CSF is going to be dark because it's free-flowing, whereas edema is not going to be free-flowing. And it can really do a good job of gray-white differentiation. Just look at the putamen and the head of the caudate. They really stand out. And let's compare this to a T2 image. So again, it looks just like the T2 image, except that the ventricles or the CSF spaces are inverted. Okay, so here's an example of where Flair can do a better job of delineating lesions near the ventricles. So we've got our T2 image here. We've got something causing edema, and it comes right up against the ventricle here, and it's really tough to tell whether or not this is the ventricle, or is it completely obliterated due to the edema. It's really hard to tell. But if we compare to Flair, we can see nice delineation here between the area of edema and the actual ventricle. Moving on to GRE, or gradient echo, you'll also hear about this referred to as susceptibility weighted imaging, or T2 star. And technically these are different sequences, but for the purposes of our talk, we're just going to consider them all as one. So here's our GRE image, and how do we recognize it? Metals are dark, so things like blood, calcium, other types of metals are going to show up on GRE. And what do I mean by other metals? Well, there have been cases, for example, of Wilson's disease where we actually can pick up on the copper deposition in the brain. What is this useful for? Early hemorrhage. Not many sequences can pick up on early hemorrhage. This one can. old hemorrhage. So old hemorrhage secondary to deposition of hemosiderin. So let's pull up another image here to compare. And just by looking at it and what we've been talking about, can you tell what sequence this is? So we've got myelin here, which is bright, that's fat. CSF is dark, so it's gotta be T1. Okay, so let's compare. Here you can see we've got an area that looks sort of edematous, but we're not really sure why. But if we compare to GRE, we can see quite clearly that this is an early hemorrhage, and that's why this sequence is so important. Moving on to DWI, or a stroke service's favorite sequence. DWI stands for diffusion weighted imaging. More on that later and what ADC means. DWI is hugely important because it is the only sequence that can pick up on early ischemia due to an ischemic stroke. Another very important thing about DWI is it's a sequence that can be performed very, very quickly, whereas many other MRI sequences can be quite slow. So how do we recognize it? Fluid restriction is bright, which stands for cytotoxic edema. So right here we have some bright signal. And what do I mean when we're talking about fluid restriction and diffusion? Well, DWI is basically measuring the Brownian motion of water molecules, and it's helpful to think of only the water molecules in the extracellular space. So what happens when we have an area of ischemia, the cells in that affected area are going to start swelling. That's cytotoxic edema. And what happens because of the swelling, the extracellular space starts to shrink, and that gives our theoretical water molecules diffusing around in that space less space to move around. And so we would say they're restricted. So when we see an image like this, what we would say is we have an area here of hyperintensity, which is indicative of fluid restriction, secondary to cytotoxic edema, secondary to a likely ischemic stroke. Very important, you must correlate these findings with ADC. And ADC stands for apparent diffusion coefficient. And the way I like to think about DWI images is as if they were a stack of pancakes. It's multiple images layered on top of each other to give you one image. So one of the images is ADC, which I like to think of as just the raw data. And then there's also a T2 image pancaked on top of it to give you some anatomic detail. So what can happen is if you've got an area of very high intensity in T2, it can shine through the pancake stack and trick you into thinking you've got an area of ischemia, when if you went back and looked at just the raw data, you wouldn't see it. So on ADC, fluid restriction will be dark, and again, we're using this to rule out T2 shine through. So it's useful for ischemia, abscesses, and seizures. And let's compare to our ADC. So bright on DWI, dark on ADC.